So, number one from yesterday, what is meant by the expression action at a distance? Sort of a warm-up one, hopefully, although it's always caused some problems over the years. So, anyone want to volunteer? What do they mean by action at a distance? Or I even would like to say force at a distance. Jake's excited.
When one body of mass can exert a force on another without being under contact?
Absolutely, perfect. When one body can exert a force on another body or object without being in contact with each other. Perfect. So how does the concept of a field eliminate the idea of action at a distance then? Like if you've got object A, I'll just draw object A here and object B here, and how does object A exert a force on object B if they can't be in contact? Well, the idea of the field is that, and I have to draw it even farther, right, is that object B is touching what? The field. Object B is in contact with object A's either gravitational field or electric field or what have you. So it eliminates that distance kind of thing because it is in contact with something. So really, as I was saying yesterday, the idea of this field, does the field exist? Well, it does, but does it physically exist? Like, you understand the difference what I'm saying?
No.
It's kind of like a model. It's kind of a way of explaining what we see, and it allows us to have that force. There is a contact because we have described it using this field.
But we don't know what it actually is yet, or what?
Like there's no physical structure there, right? Like it's not. There's no molecules that are lined up in a certain way. Is it there? Yes. Is it physically there? Not so much, right?
So what's an example of action at a distance?
Like the moon is attracted to the Earth 24/7, right?
Okay.
The Earth is attracted to the sun all the time. There's that force, right? But there's no... Is there anything between the sun and the Earth that holds us in place? Like anything physical?
Yes.
Mercury.
The air.
There's no air in space,
Whatever.
right? But the field... Does the field exist? Well, of course it does. Otherwise, we'd be spinning in space. But it's not physically there.
Maybe it's not the same air that's in Earth, but it's still air.
Maybe. Actually, the ancient people did think that. They thought there was something called the ether. They were either right or wrong. They were wrong. How are gravitational and electric fields similar? And then I'm going to also ask you how they're different. And somebody who came to see me yesterday at the desk. Who was that? Someone came up to talk to me yesterday. Oh, who was it? Was it you, Zach? Can't remember. Who?
What is me?
Was it you, Jake?
It was.
Pretty sure. Anyways, whatever, it doesn't matter. Okay, so how are gravitational electric fields similar? They're both fields, first of all, okay, that's the obvious one. They're both fields. They all can also both attract. They can both attract. They can hold objects in place. They can pull on them. They're both vector quantities. There's lots of similarities. Now, the question isn't there, but I want to ask it. How are they different? So how are they different? What's the number one difference between gravity and electric fields? I did explain this to someone yesterday. Was it you, Riley, that came to see me? I drew pictures on their diagram. It was Chris, it was you. Yeah, that question, yeah. Yeah. No. Well, no, it might have been, well, we discussed this, because remember I said that I added on to my answer. Yes, gravity can only attract, whereas electric fields can repel. Electric fields can repel, gravity cannot repel. It can only attract. So that is one major difference. Not the question, but still certainly something worth knowing.
But can the electric field still attract?
Yes, electric fields can still attract, absolutely. All right, number 4. Why is an electric field considered a vector quantity? It's pretty easy, because it has a magnitude, it has a strength, and it has a direction. That's the definition of a vector. It has a magnitude, it has a strength, it has a direction. Okay, what are electric field lines, and how do their directions compare with the direction of the force that acts on a positive test charge in the same region? A hard-sounding question, the answer is pretty easy. What are electric field lines? They're kind of like vectors in that they look like arrows, but as Joey pointed out yesterday, they are not.
Oh, those really long ones?
Yeah. So what are electric field lines? They are lines that indicate what?
The force of a
How about we use the word strength?
strength,
Okay, the strength of
the gravitational field.
electric field lines?
Sure.
They indicate the strength of the gravitational?
No.
Yeah.
The electric field.
Electric field strength, absolutely. And how do they indicate that, Jason? Like
The density.
density, how close they are together, exactly. How close the electric field lines are together indicates the strength. I think that's a pretty good answer. Now, how do their directions, how do the direction that these electric field lines point compare? Are they the same or are they different with the direction of the force that acts on a positive test charge in the same region? So, in other words, if I've got object A here, and I've got a little tiny test charge way out here, what direction would that test charge go? Would it go towards A or would it go away from A? Absolutely, Joey. It depends if A is positive or negative. If A is positive, well then the object would go that way. And if A were negative, I'll just redraw here, then the little positive test guy would go towards, wouldn't he? Right? So how do those red arrows compare with the electric field lines of A? Well, if A is positive, which way is the field? Out. Is that not the same? And if A is negative, where do those lines go? Towards. Is that not the same?
No, it's
That's not the same as that red right there? Like these are two different situations, right? The arrows of this electric field, I'll get you in a sec, Jake. The arrows of this electric field point in the same direction that the positive test charge would go, and the arrows of this A negative field strength point towards it is the same direction as this positive test charge. That looks like a negative. Let's be positive. They're the same. They're the same. Why? Because electric field lines always point in the direction that a positive test charge would go. That's the definition of it. They have to be the same. That's how it's defined. Jake has a question. Maybe I've answered.
Positive test charges and like negative test charges, are those represented protons and electrons?
Could be, yeah.
Okay, so like in theory, could a positive electric field, if it amasses enough electrons, could it become negative?
Sure. And then it would change the direction of the field, absolutely. Interestingly enough, the Earth's magnetic field is changing direction. The Earth's magnetic pole is actually changing location. It moves about 10 to 15 kilometers a year, I think it is, and can wander anywhere up to 80 kilometers on a daily basis, depending on currents in the Earth's inner core. So, well, your compass can actually be out by, 8 kilometers is not that much. But anyways, that's sort of, well, it's a long way if you're walking, you're right. Especially if it's cold and you're out in the magnetic North Pole, right? Yeah, absolutely. Wear a tooth. Okay, number 6. How is the strength of an electric field indicated with field lines? I think we've answered this already.
Yes, with the first one.
It's the density. It's how close the lines are together, right? The closer the lines are together, the stronger it is. It's when they're far apart that they're weak, right? Dana's probably going to be hearing this because she's probably watching on a daily basis, right? We should say hi, Dana, to her, see if she hears us. Yeah. Now she'll feel sad because she's not here as she heads out to the beach. Yeah. How do the electric field lines appear when the field has the same strength at all points in a region?
Parallel.
Parallel, or if you want to be fancy mathematical, equidistant.
Whoa.
What does that mean, equidistant?
I didn't know that.
Equidistant? Oh, how do you spell parallel?
No, no.
Oh, equidistant? Oh. Equidistant. Equidistant. Yeah, no, equidistant. It just means the same distance apart, right? That's all it is. Oh, that's a cool word. You should try to slip it into your conversation wherever you can.
Well, equidistant.
People, yeah. Ooh.
Alright, Jake, how's that equidistance going?
That sounds like something you have to go see the doctor about.
Well, you are gonna-
Some sort of rash or something. Okay, now think and explain generally means a little bit harder. How is it? We've answered this one.
This is another.
I remember why I got the question in my head. How is an electric field different from a gravitational field?
Right.
You were talking and explaining.
Well, it wasn't in number 3, but I put it in, right?
An electric field.
How is an electric field different? An electric field can attract or repel.
Gravity.
Gravity can only attract. Exactly.
I knew that one.
The vectors for the gravitational field of the Earth point toward the Earth. The vectors for the electric field of a proton point away from the proton. Explain it. Well, we're talking about 2 different kinds of fields here, so big deal. They point in different directions, right? Gravitational field of the Earth points towards the Earth. How come? Gravity attracts. Why does it says the vectors of electric field? That's not a good idea. The arrows. An electric field point away from the proton. How come? Because that's the direction that a positive test charge would go. Positive electric field point away. Now that's merely just convention. If we had chosen to use negative test charges, then everything would be opposite. It's just a convention.
Free.
A free electron means that it's not attached to anything. It's just sort of like a free agent, can kind of go anywhere.
Just floating around.
Just floating around, having it,
Someone to come pick them up.
yeah, not attached to anyone or nothing. So if a free electron, oh yes, now I remember this question. Oh, this is a dandy. If a free electron and a free proton were placed in an electric field, how would their accelerations and directions of travel compare? I'm going to ask you to partner up and discuss this for a second. Okay, but I'm going to explain it a little bit with a diagram. Okay. Listen carefully. Listen carefully. So I've got object A. It's creating some field. Does it matter whether A is positive or negative? I'll leave that up to you. Okay, and I've got a proton here, and I've got a electron there. Which way, if A is positive, which way does this one go? Away, and this one goes that way. But if A is negative, then the positive guy goes towards, and the negative guy goes away. But I want to know, how would their accelerations compare? Would they be the same? Would one be greater than the other? Which one would be greater than each other? Let's just say they're plopped in place, like someone's holding on to them. You can't physically do that, but you sort of like hold on to them and then you let them go.
The one going towards.
You talk about it amongst yourselves. Spend 2 minutes talking about that. I hope that you've actually maybe thought about some chemistry here as well.
Oh, Jason.
Okay, who thinks they've got a good answer? Jason?
I like
Jason,
it.
I trust.
Peyton? No?
Yes.
Yes? Okay, let's hear from you, Peyton.
Opposites attract.
Okay, give us the whirl. What do you think?
That's all I have.
Pardon me?
That's all I have.
Well, it happens so fast I didn't even hear it. I want to know how their accelerations compare.
Jason's how they look.
I trust Jason.
Okay, Jason?
Yes.
The one moving towards it will accelerate faster because the force will be greater the closer you get towards it.
Okay, so you're saying that this one is going to be greater,
And the other one.
and that's because as it gets closer.
Why is that one going to be greater?
Is that what you're saying? Oh, sorry. Oh, the other one. I think I heard that right. I just wrote it in the wrong spot. So you're saying that this one is greater,
Yeah, because it's getting.
and that's because the closer it gets, the field, Joey? The closer it gets to object A, the stronger the field, which would imply a greater force, which would be a greater acceleration. Does that sound reasonable?
Good idea.
Jake, would you agree?
Well, if we want to get technical,
I do.
could, in both instances, we think that the electron would accelerate faster because in chemistry, an electron is like 1/1000th the weight of a proton, so the same force would be able to act much more strongly.
Excellent. Excellent. Jake's point is that the electron is what?
Like 1/1000th the weight of a
The mass is ridiculously less. Boo-hoo! If I had tissues, I'd distribute them. Okay? The electron is much, much, much less. I didn't know it was 1/1000th, but it's really tiny, right? And so a much smaller mass means much less smaller force. So Jake is likely right that in both cases, it doesn't matter whether this is positive or negative, this is likely going to the mass of the electron and how small it is likely going to mean that it's going to accelerate faster. However, I think Jason's answer and his group's answer is the answer is what the textbook people really wanted. If they had said a single charge, right? Comparable masses. If they'd said equal masses, then Jason's group would have been bang on. I think that's the answer they're looking for, but I've got to give it to Jake's group because.
It was actually just Jason that came up with that.
Yeah, that's good. That's good.
Thanks, guys.
Yeah, it's probably just Jason.
Yeah, so what do we write down?
Let's just accept it.
Well, both.
We're in
Jason said that the one that is being attracted, because as it gets closer, the field strength does what? Increases, and therefore the force increases, and therefore the acceleration increases.
What was the first one before force?
Put the pen down.
Can't ask her to shoot.
Just put the pen down and listen. Don't try to write down individual words. Listen for the understanding and then put it in your own words, Peyton. Are you ready? Okay, so listen. I'm going to explain it again. Okay? Listen to understand.
You're not supposed to repeat yourself.
The one that is attracted should be accelerating greater because the closer you get, the field strength, Peyton. The stronger the field strength, which means you're going to have a stronger force, which means you're going to have a stronger acceleration. Faster acceleration.